annoying, right? What if we could get rid of this sound? What if we could get rid of all mosquitoes on Earth? Wow. Unfortunately, this is not just a matter of annoyance. This little creature is still responsible, or still the main vector of transmission of many diseases such as malaria, dengue, Zika. Diseases that are still infecting millions of people and killing many more. So, who are the victims of these diseases? Well, mainly children. So think of a stadium full of children. Now think of 9 stadiums full of children. This is the number of children who are still killed by malaria per year. So what can we do about this? Is there a solution? So if you think about the fact that if mosquito is the main transmitter of malaria, if we eradicate mosquito, we'll eradicate malaria. Actually, many methods, many approaches have not been that successful. So for the past years, people have been thinking of modifying mosquitoes genetically so that you can now prevent the transmission of malaria. So how can you do that? For instance, by converting the progeny, or the female progeny, converting them all into males. So this way you will be reducing the number of females available for reproduction, and at the same time you will be actually eliminating the real vector of transmission, which is the female. Because if you know, it is the female that sucks up your blood, because it needs to feed its eggs. So the idea is that by releasing into the wild, into the nature, mosquitoes that are genetically modified, they will be mating with their counterpart, their natural counterparts, and therefore converting their progeny, their female progeny, into male progeny. Great, this should work. So there's only one thing though we have to keep in mind, that this strategy would only work temporarily. And why is that? Because of this number. So mosquitoes, just like us, they have 2 pairs, or have their chromosomes organized in pairs. They have, therefore, for each gene, they have one copy that comes from the mother, one copy that comes from the father. So when it's their turn to pass on their genes to their progeny, so only one of these copies is going to be passed on. So there's 50% transmission rate for each copy of each gene. So this means that after a while, if here you have the genetically modified mosquito in green or bluish green, and the wild type, the natural mosquito that is in the wild in black. So after a while, since only one copy is going to be passed on, or half the progeny is going to have the gene, the genetically modified gene, the other half is not going to have it. So after a few generations, what will happen is that the genetically modified gene is going to just eventually fade out. It's going to disappear. So it will only work temporarily. So what do we need to fight this? What we do to make sure that this genetically modified gene or mosquito is going to be there out there in the wild forever, so that we can actually kill and eradicate the species? So we need this number, or something very close to this. We need that the transmission rate of the genetically modified, or the transmission rate of this gene that is going to convert female progeny into male is going to be passed on from generation to generation, so that finally the genetically modified mosquito will take over the natural population. And that will be a way of eradicating mosquitoes from the surface of Earth. How can we get there? How can we do this? We can do this, we can achieve that level of transmission rate through a new technology called gene drive. So what happens in this gene drive technology, what happens is that you not only modify or insert in the mosquito the gene that is going to convert the female progeny into male, but you also attach these 2 little pieces that ensure that that gene is going to be passed on to the other generations. And this has been tried for a long time, and people were not successful. We didn't have a way of transmitting this genome. We didn't have a way of reproducing this gene drive that sometimes also happens in the wild, but we wanted to be able to do it ourselves. It was only until recently that we were able to do it. And how? Or just to make sure that I want to say that this is really groundbreaking, because this gene drive technology will finally allow you to change the genes out there. So the fact that we could not transmit this genetically, or could not expand or spread genetically modified species permanently, has been a delay in our approaches to that I'll tell you about. So, such as this. So we now have the possibility through this gene drive by spreading the genetically modified species in the wild, we'll have the chance of not only eliminating vector-borne diseases as malaria, as I just told you, we can also enhance the productivity of crops. And how do we do that? By increasing the sensitivity of weeds, the natural weeds, increasing their sensitivity to herbicides. So by doing that genetically, you can, so the weeds are natural, they're a wild plant out there, and we can now have the chance of spreading the genes we want into the wild population of weeds. So we will be able to increase their sensitivity to herbicide. The same way we will be able to eliminate invasive species like rodents from islands like Galapagos. So this is really a big deal, because not only can we now design organisms genetically in our lab, but we can also put them out there. How can we do this now, and why couldn't we do it before? Because we didn't have this tool, CRISPR, that you might have heard of this morning. So CRISPR, what is CRISPR? This is a technology, a very recent technology from 2012, 2013, basically, and CRISPR is like a molecular scissors that will allow you to edit and change your DNA. So this means that not only can we now read our DNA through genome sequencing, and you've heard from Jeffrey yesterday, in 20 years we went from the cost of reading your genome from $3 billion to $100. So not only can we do that, but now we can actually change this DNA. We can edit it. So if we spot a mutation in our genome, we're able to erase it. And this is incredible, and can be a tremendous value in trying to fix mutations that can lead to genetic diseases. One of these examples, for instance, is muscular dystrophy. So this is a genetic disease that affects 1 in 5,000 boys. What happens is that there's a mutation in a gene, in a muscle gene, dystrophin, and their muscle is just weak. So after a while, they don't have enough strength even for the heart to pump. So they used to die around, it's a fatal disease, they used to die in their teens. Now with some external support, they will be, if they're lucky, they can make it to the 30s. So finally, this could be CRISPR, and the fact that we can edit genes could be a solution for fixing something like this, for this disease. And it just turned out that this experiment using CRISPR to edit the genes, the specific gene that causes this disease, has been tried in dogs, in this kind of dog, this beetle. And what we just found out is that the muscle cells of these dogs were actually fixed after being repaired by CRISPR. So they're both their heart cells and muscle cells of the body, they could be repaired. So which brings great hopes of cure for this disease, as you can imagine. Even more interesting is that not only can we read, we can erase and change DNA, we can also write it from scratch. This is like a whole new field that is called now synthetic biology or synthetic life, where we can just program it. We can put all the DNA letters together as we wish, but of course based on what we have learned from reading and studying genes. So I like to see the genome as a dictionary, as a set of words. And this is the number of words we have for, oh, this looks a little different. The number of genes we have in different species. So we're around like 19 to 20,000. We have the yeast with 6,000, 17 for Drosophila. Surprisingly, mice and rice have more genes than us. Interesting, right? Because this tells us that it's not just about the number of genes or the number of words that you have in this dictionary, it's how you combine them. Which makes perfect sense if you think of a Portuguese dictionary, and you can write millions of stories using those same words. It's all about how you combine the words and what words you pick and in what frequency. So this is what cells do. In our body, we have 310 different types of cells. And in case you didn't know, each of these cells, or almost all of them, there are a few exceptions, but most of these cells have 2 meters of DNA inside their nuclei, and these 2 meters are the same in all the cells of the organism. So you think if they all have the same DNA, how come they become different cells? How come they can differentiate into 310 types? So it's exactly what I was telling you about. It's about the words they pick to write their own script, to write their own narrative. So if we can learn how each cell writes its narrative, we will be able to reproduce that same mechanism. We will be able to take a cell that can become any kind of cell, like a stem cell, and we will be able to reproduce and generate exactly that type of cell. I like to think of stem cells as a piece of clay. A piece of clay that can be molded into any kind of piece that can have a specific tissue. And why is this important? This is important that we understand that mechanism again so that we can reproduce it. And this is something that happens naturally in our bodies every day. So every day, at every second, we have cells in our body that are dying and that are being renewed. I like to think of it as when we go to bed and when we wake up. Well, when we wake up, we're not exactly the same person that went to bed, because many of the cells are completely different. We have cells that last a life. We have cells that last only a few seconds. Skin cells, they're renewed every 4 weeks. So, and the amazing thing about learning this process of converting the clay into cup was also in the hope that we could learn the reverse, turning a cup into a clay. And this is what iPS cells are about. These are cells that are made of skin cells, for instance, and this is something we started to learn by understanding the function of this gene. So nowadays, we can take skin cells and take them back to turn them back to clay. So the iPS cells is now a technology that offers great potential. And why is that? So think about this. If you can take a skin cell and turn it into a stem cell, and if you know how to turn the stem cell into an insulin-producing cell, then you'll be able to turn a cup into a plate. So you turn your skin cell into a stem cell. From the stem cell, you differentiate it into the type of cell you want. So why is this useful? Think you're at home. You broke all your plates, and you don't have a piece of clay to make more plates. You take your cups, you turn them into clay, and then you make your plates, your missing plates. And this is what happens, for instance, in the cell therapy or the cell replacement therapy. For instance, in diabetes type 1, people, or the cells of people with this disease, that the cells should be producing insulin, and they do produce insulin in this type of disease, but they just start dying. So you have to replace them. So you can now take skin cells of that patient, you can turn them into stem cells, and then make more cells of what they really need. So this technology really brings great hopes in the field of regenerative medicine. So for cell replacement therapy, as I told you, and if you combine it with CRISPR, CRISPR will allow you to also tweak and change the mutation that was causing the dying of the cell to die. So you can take your cell, your skin cells of a patient, you can turn them into stem cells, you can correct the mutation, and then you can multiply the cells and differentiate it and have a huge number of insulin-producing cells that you can replace in the patient without causing any rejection of the tissue. So not only can you do that with cells, but you can also use these stem cells to then produce other specific cells that could be used for 3D printing of organs, which, as you know, there's a huge shortage of organs these days, and this could be a great solution for your truly personalized medicine. If you combine also iPS cells with the knowledge of your own genome, we can now link, for instance, drug treatments to our knowledge of genomics, with what we call pharmacogenomics. What it consists of is that you can apply a drug to your own cells. So you take skin cells, you can make any type of cell, like liver cell, you apply the drug, and since we can read your genome, we can connect genes to response to drug. And this is a great field that is keeping on development and has great promise. So we can now, for instance, make from your own cells, we can make any type of cell. So we can have a chip that is called the human on the chip, where you can have your liver cells, you can have your lung cells, you can have your kidney cells, and you can apply the drug. And you see not only how each of these population of cells responds to the drug, but you can also see how they all interact together, because you know that sometimes you try to cure one thing and then you start another problem elsewhere. So now you can reproduce yourself, like your mini you can be on a chip that can be tested for drug development. So you can imagine that this will really greatly increase the speed of the process of drug development. It will not involve animal trials. You can lead to great success rates and lower the risk of adverse effects. If you can take a skin cell and make any kind of cell, this means that, well, maybe we can make egg cells. And we can. So in mice, so this image is the image of egg cells, artificial egg cells of mice that were generated exactly how I described to you. From skin cells of the mouse, we could make stem cells, and from those cells, make egg cells. These cells were fertilized, and they actually gave rise to small pups. So it's possible. How about humans? They'll think, oh, that's in mice. How about humans? Well, it turns out that we can now also make mature egg cells, or still immature, not completely mature yet, but we're getting there. I always think that human being is a very stubborn animal. And if we want to do something, we'll make it work. So soon we'll have to start thinking of questions like, should a child have its own child? Because now we can do that. Should grandparents have children if we only need their skin cells? Should we have progeny of that person? So there are all these questions that are now being raised and can challenge even the concept of family. So you can see that all these different technologies, which are exponential, if you start combining them, then you go beyond exponential. I think you go explosive. You now can edit any kind of organism at a very fast pace. It's accessible to all. It's cheap. You can now edit organisms and you can spread them in the wild. So you can really start integrating with the ecosystem for the better or for the worse. You can do your iPS cells. You start testing all the drugs. It's going to change the pharma industry. You'll be able to create organisms, for instance, the organisms that will produce fuel or different types of energy. So this is going to have a great impact. So we can say it's truly genius what we can do today with all of these approaches. However, we should sometimes pause and think. There are a few questions that can come out of all these new technologies, right? We recognize the technology's potential, but as with all great technologies, with great potential, there's also great risk. And with risk, there's fear and there are questions. And questions are not always black and white. These kind of questions sometimes are kind of gray. For instance, what will happen to the ecosystem if we do eradicate, if we do exterminate mosquitoes? We don't know. Nobody knows. We have to think about this. Maybe we think they're just not needed on this planet, but maybe they are playing a role and it's going to affect something else that is going to come back to us. Where do we draw the line between preventing and curing disease by editing genes or actually improving features, improving traits like your height or changing your eye color? Or where do you draw the line? What is acceptable? Where is it acceptable to use these genetic editing tools that we now have? Also, whose artificial eggs should we allow to generate if we go that path? It can be great for cases of infertility, but who should be allowed to have their skin cells turn into eggs and progeny from that? Another, of course, big question about gene editing is, do I have the right to change the DNA of my child, of my baby? And again, going back to the mosquito case, do I have the right of extinguishing a species? What I'd like you to think about is that it's not all about right. Think about responsibility too. It's these two words and how they come together, and it's easy to focus on only one of them. If we're stuck with the, do I have the right to exterminate mosquitoes? Sure, but how about, don't I have the responsibility of saving those 9 stadiums of children? Do I have the right to change my baby's DNA? But don't I have the responsibility of preventing a disease that can be fatal? And I knew that I had the technology in my hands to prevent it. So I'd like you to think of that, right and responsibility. The same way that you should think of misusing technology or missing the use of technology. So misuse versus misuse. I think this is very important, and it should be applied to all technologies we're developing these days. And to do so, we need you. Why? Because all of these technologies are going to have an impact in you, in your family, in our society, but also in your field. Because as remote as you think that you might be from genetics, you're not. Sooner or later, genetics is going to have an impact on your field. And not only is genetics going to have an impact on your field, but your fields will going to have an impact on genetics. You can do something about it. So you can be part of the solution. And this is something that I really like you to take with you. This message that, again, as remote as you think you are, you're not. And you do have, in all your fields, you have a role you can play in this. Not only as an individual, but also as an expert in your field. So every time you hear the news now about genetics, and just don't think, oh, that's genetics. Just think, how is this going to impact my field? How can I have a contribution, not only as an individual, but also as an expert in this field? Because we're not going to solve all these questions, all these great questions. We're not going to solve them alone. We need to be all on the same page, and we need to have the views of everybody. And this is the only way we're going to decide how we want to genetically modify our future. It's in our hands, which are also your hands. So, thank you.
Sílvia, thank you so much. Congratulations on the way we'll talk. We're going to do like a very brief 5-minute Q&A, all right? And I'll start. I was listening to you speak, and I always have this feeling when I listen to smart people. Like I feel smarter than me. But one of the things that I always get is I want more than your experience and the work you've been doing. One of the questions I always want to ask is like, in your day-to-day operations, so to say, in your work, what are the challenges that you face? Is it just the technology, or is it also society, the people? Because we have all these questions. Should we? Who wants to eat genetically modified meat? And how hard is it to actually put it in the market? Or how hard is it to use CRISPR in the future? Will it be hard? Like, will people actually reject these kinds of solutions? So in terms of challenges, what do you see and how do you deal with it?
Well, primarily focus on the technical challenges, right? But you always have in the back of your mind that you're doing this for a purpose, and you have to believe in that. If you don't, there's no way you can do it. And you don't want to do this to convince people that they need it. You have first to be convinced, and you want to explain why you believe in what you do. You don't want to convert people, you want them to understand the need. And you also want them to be part of this decision, should we do this or not. I can guarantee you no scientist wants to take these kind of decisions on his own.
Right. And have you ever had that moment where you go, well, you just made this awesome thing, I wasn't really expecting to now have all these other obstacles that are not related to the technology itself? Have you ever had a moment where you dealt with that?
Myself, I didn't have to deal with it, but it's something that we always bear in mind. But again, I think you can. What's happening today, the kinds of opportunities, the possibilities, all these technologies that we start combining and can bring, it's pretty incredible. So yes, I can imagine that you're not surprised from one moment to the other, like how about surprise, but you start thinking, you start understanding, even for people in science, you start understanding like how big this can be.
All right. Okay. So questions for Sílvia. By the way, who stole the mic? Last time I saw it, was it? Yeah, it's right here. Okay, cool. So who has questions they would like to ask? Yes. All right. So let's do it. Let's see if I can do that. That's good. You guys speaking to it?
So I listened to your talk. That was very interesting. But I would just like to ask regarding some applications like stem cells and CRISPR. We hear a lot about it, and here there are certain breeding grounds for it, like Panama, like Mexico, Germany is doing a lot of stuff in stem cells, also with Genetically. Is there a mass market application for stem cells specifically, or do you put it on the line and you still have to go to the Panamas and the Mexicos of the world to get real stem cells, for example, in your application?
If there's a market in
real market application, do you see, for example, in the next 5 years in Portugal as a recommended course of treatment instead, for example, of an MCL surgery? Do you see it replacing, for example, just in a few shoulder surgeries, stuff like that?
Yeah, I do. Of course, you always have to make sure that you have to do your trials, you have to make sure it's safe, but I do think that there is a future in stem cell for cell replacement therapy.
All right, we have time for one more. Who has one more question they would like to ask? Yes, right there, right in front of you. So catch the mic. Yeah,
this is okay. It's good for short talk. It's like we spoke about a lot of exponential growth here. I actually think when I hear you speaking, when I see a lot of other people speaking, and we see genetics and we see technology, that we are all on the brink of the exponential evolution of mankind. Have you ever discussed this seriously? What's like in the next decades to happen to the mankind and the next century? Centuries maybe it's too far away, because you are thinking still in ethics, if we can do or we shouldn't do, but I'm sure that we will do. It's a question of time. So.
No, that's my impression too. It's, as I was saying, I think the human being is a very stubborn species, and it's gonna get there. We still have to deal with, for instance, with CRISPR, we have to deal with a lot of secondary effects, and we still have challenges, technical challenges. But I think eventually we'll get there. And ethically, you'll try to regulate it the best way you can. But that's why it's so important that everybody's involved, because we have to look at the different aspects of the question, and not even just like us as a society, but also like us as inhabitants of this planet. And there's a lot we have to think of in advance. And that's why, for instance, like computing biology, like will be better. We'll have to really think of all sorts of impacts this can have. And it's not easy. That's why we need everybody involved.
All right. Thank you so much. A big round of applause again.